All right. Hello, human biology students. So, in the last lesson, we talked about metabolism. We talked about how glucose can either go through the aerobic pathway or the anaerobic pathway in order for us to be able to make energy for everything that we need to do. Well, in this lesson, we're going to look at enzymes, which are really important for many of the steps in metabolism. And enzymes are not only in metabolism, we actually have them all throughout the body because enzymes are very important for making chemical reactions occur faster. So before you continue with this lesson, I highly recommend watching two videos. One is called Enzymes by the Amoeba sisters. So I've mentioned this channel before on YouTube. It's very helpful. As well, there's another channel which I think is also pretty helpful. Professor Dave Explains. And this video is called Enzymes, Nature's Factory Workers. So both of those videos I'd watch before continuing with this lesson. Now, if we talk about enzymes, I'll just go to my PowerPoint slides here. So we talked about metabolism, and metabolism has many important enzymes in it. So what is an enzyme? So we say an enzyme is something that speeds up chemical reactions. And the way that it does that is I've got an enzyme pictured here in blue. Okay. Anything that binds an enzyme is what we call a substrate. So in green, we've got the substrate. So a substrate binds an enzyme at a specific place called the active site. Okay, and that's highlighted here in light blue. Enzymes are very, very high maintenance and very specific. So this enzyme will only ever bind this specific type of substrate, not any other kind, right? And its shape, the shape of the active site is so specific for this substrate that the analogy they usually use is it's similar to a key and a lock, right? So they call it the lock and key model, where the active site of an enzyme is so specific in its shape for a specific type of substrate that it's similar to a key that goes in a lock, right? So we know that a specific key will only open a specific lock, right? That's the same for a substrate and the active site of an enzyme. So enzymes are specific to their substrate. So there's specificity there. Okay. Now, if we actually look at one of these images, right? So a substrate will bind the enzyme at the active site. It becomes this one unit, which they call, very unoriginal name, the enzyme substrate complex, because now it's a complex, it's one unit. Okay. And this allows the enzyme to help in converting that substrate into what's called the products. So the thing that binds the active site is the substrate. The things that leave are the products. Okay, so we always have a substrate that binds to an enzyme and products that leave the enzyme. Okay, so, hey, stop it. Sorry, you guys, those are my cats. So, when we talk about enzymes speeding up chemical reactions, if we actually look at, the amount of energy that we actually need and hold, and how enzymes help to speed up chemical reactions, they speed up chemical reactions by lowering what's called the activation energy. So I've got a substrate just like this. Okay, this might be lactose, and this enzyme may be lactase. By the way, you'll know you're dealing with an enzyme because the end of the word is ASE, right? So you might have enzymes that we come across called lipase, protease, amylase, ATP synthase. Okay, whenever it's got an ase suffix, so ACE ending to the word, it is an enzyme. Okay, when you hear ose, O-S-E, as the suffix for a word, that's usually telling you you're dealing with a sugar. So for example, let's just pretend I've got a lipase enzyme, which helps to break down the sugar that we find in milk, lactose. Okay, that's a disaccharide. So there's 2 monosaccharides bonded together, my disaccharide. Right. So substrates, remember that bonds have a certain amount of energy. We know that because when we look at high energy bonds, like in ATP, right, we can break those bonds to actually release energy. Okay. So because we've got a bond here, we've actually got a certain level of energy. Now, in order for me to actually be able to break this bond, I need some energy to do that. Okay, that's what we call the activation energy. It's the amount of energy that you actually require to break that bond in order to actually make your products. Okay, now if I've got substrates, my substrates hold a certain amount of energy in their bond already, and I require just a bit more energy to break those bonds so that I can actually have my products. Okay, you'll notice that when an enzyme is involved, okay, an enzyme actually lowers the amount of startup energy that you actually need in order to break that bond to create products. Now, if I had no enzyme, so if I didn't have lipase, okay, I could still break down, so the chemical reaction where lactose sugars are being broken down into their products, that would still happen. It would just take a really long time, okay? So chemical reactions in the body, all of them will happen on their own, but some of them will take so long, so ridiculously long. In fact, some chemical reactions might take a lifetime to actually occur. So enzymes are really important because we actually need them to happen in a short amount of time because we need the products, right? So enzymes are very important. So yes, without enzymes, I'd still have a certain amount of activation energy. That obviously means that I need to find a lot more energy in order for this reaction to take place. That's part of what makes it take longer, right? So a chemical reaction on its own takes a lot longer. And enzymes lower that startup energy so that you can have that chemical reaction occur faster. Okay, so enzymes speed up chemical reactions. So we call them something called a catalyst. Okay, and the fact that as soon as this enzyme binds its substrate and releases its product, notice that the enzyme has not changed at all. The enzyme stays the same, and I can actually reuse this enzyme if I've got more substrate to bind another substrate and have all of this happen again. So enzymes are reused. Enzymes do not get destroyed. They stay the same throughout the chemical reaction process. And because we can use them over and over again, and because they help to speed up chemical reactions, we call them catalysts. 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 Okay, so enzymes are important. They are a type of protein. So the elements that you'll find that make up most enzymes, so not all enzymes will be protein. You can have some that are actually made of nucleic acids, okay? But most are proteins. So they're going to have the elements carbon, hydrogen, oxygen, and nitrogen. They're going to be made of amino acids folded in on itself in the shape of proteins. Okay, so enzymes are protein catalysts. They speed up chemical reactions by lowering the activation energy. They have a specific active site that's specific to a substrate. They bind the substrate to make what's called an enzyme substrate complex. They fit their substrate in a specific way, and we call this the lock and key model. And they turn the substrate into what's called products. Okay. Now, we did talk about the fact that enzymes are very fussy. Enzymes are very high maintenance. They're very, very specific, not just for the type of substrate that they'll bind to, but also for a whole heap of factors. So two of the main factors that usually come up are temperature and pH. Okay, so they're specific for temperature. So if you think about our body, right? Body core temperature is about 37 degrees Celsius. So majority of the enzymes in metabolism, in many other chemical reactions that are happening in our body, their optimal temperature is in and around 37 degrees Celsius. If you crank up the heat, so if somebody starts getting a fever, their body core temperature increases, notice what happens to the rate of reaction, right? That's because enzymes, remember they're proteins, if you crank up the heat, you actually start to ruin the structure of proteins. We call that denaturing. Okay, so if you have a protein like this, it's folded in on each other, it's got a specific function, you add heat to it, you actually start to break apart some of the bonds that keep it folded like this, and it just ends up like a loose noodle. Okay, this is called denaturation. So denaturing happens because of heat, right? So if somebody gets a fever, okay, a little bit is still okay, but as soon as you start going well beyond your 40-degree mark, okay, your enzymes start to denature. So you have less and less chemical reactions happening that you actually need, and that's a problem. And this is why if you have a fever that's not going away, a fever that is increasing in temperature, they tell you need to go to the hospital, okay? It can be very dangerous. The reverse is also true, right? If this enzyme pictured here has an optimal temperature range between, let's say, 35 and 42, okay, then anything below that as well is going to decrease enzyme activity. And the reason for that is, remember that nothing in the world is actually standing still. Everything is constantly moving. So in order for a chemical reaction to occur, you actually need your substrate to collide with an enzyme so that they can actually bind, okay? If it's 0 degrees, okay, chances are nothing's going to be moving, nothing's going to collide, and you're not going to have any chemical reactions. As soon as you start adding heat energy, remember heat is a type of energy, so if you add heat energy to all of the particles, to your enzymes, to your substrate, they move around with, a little bit more, a little faster, add even more energy, they're moving around even faster, add more heat energy, they're moving around even faster, and so the chances that they'll collide is a lot higher. So the more heat that you add, right, the better it is until you reach the optimum temperature that they love. That's when you have the most amount of collisions and the most amount of product being made. And then, of course, after that, the temperature is too high for the enzymes and it starts to denature the proteins, and that's a problem. Okay, so each enzyme will have a specific temperature range that's optimal for them. Okay, so some will have an optimal temperature in and around 37 degrees, but of course if you think about our stomach is very acidic. It has hydrochloric acid in it. Oh, wait, we're talking about pH now. Oh, sorry. Oh, I haven't had my coffee yet. All right, so jumping to pH then, right? So similar to temperature, each enzyme will also have a certain environment in acidity levels that it likes in particular. Okay, so our blood, for example, has a pH of about 7.2. So any chemical reactions that are happening in the blood, any enzymes that help with those chemical reactions likely are going to have an optimum pH temperature in and around there, right? But if we talk about the stomach, right, the optimum pH for an enzyme in the stomach, because we have hydrochloric acid there, we know that hydrochloric acid has a pH of around 1 to 2. Okay, that's going to be the optimum acidity level for those enzymes working in that environment. So enzymes are fussy. If I were to take one of those enzymes that normally, work in the stomach, so they obviously love acidic environments, and put them in a place like the blood, they wouldn't work. Okay? So temperature and acidity is going to affect enzyme activity. Okay? Another factor that can affect the rate of chemical reaction or enzyme activity would be substrate concentration. So you can imagine if I've got 3 enzymes here, okay, each of these purple dots is my substrate, which binds the active site at the enzyme. Okay, as I increase, if I keep dumping more and more substrate, right, I'm going to go from the chances of them colliding, right, because I've only got 1, 2, 3, 4, 5, 6 maybe substrate molecules. The chances of them colliding, you know, I might have one collision every few seconds, okay? But if I keep dumping more and more and more substrate, now all of a sudden in the same space, I've got heaps more substrate particles, right? The chances of them colliding is higher, okay? So now, you know, I've got 2 enzymes maybe per few seconds that are actually binding substrate and turning into product. So now I've got more product being made. So you can see the rate of reaction increases as I keep adding substrate, keep adding substrate, keep adding substrate, until eventually, Layla. Sorry guys, I have a small kitten. Until eventually you get to the point where you've actually got all of your enzymes are completely full. They've got substrates bound to them. It doesn't matter how much more substrate I dump in this amount of space, they're all full. They're not going, it doesn't matter how much more substrate I put, they're not going to be able to bind any of these enzymes because they're already full. They're already saturated, okay? We call that saturation, okay? So saturation is when all of the enzymes that can possibly bind substrate are already full, okay? So all of them are saturated. At that point, the rate of reaction is not going to change. It's going to stay the same, okay? So substrate concentration, generally, as we increase the amount of substrate we have, it will increase the rate of reaction until saturation. At that point, we're going to experience a plateau in the rate of reaction because it doesn't matter how much more substrate we put, right? All of the enzymes are actually full, okay? Now, that's all I've got for you guys at the moment on enzymes. I'm not going to mention coenzymes and cofactors because it's a very small part, and the video with the by the Amoeba sisters actually goes into that, and that's probably the amount of detail that you probably need to know about that. So hopefully this has been helpful for you. And gives you an introduction into enzymes, which we're going to see more and more and more as we learn about the different body systems. So with that being said, I hope you guys enjoyed this lesson.